just so happens topics are local, they contagious. So it's a good coincidence. This is Sander.
Hi, I'm Tom. This is joint work with Sam Staten. Yes, that's it. And it's about non-locality, and it's about theories, generalized theories of probability. And we use these theories to study non-locality. And there's a huge spoiler on this slide. We will use effect algebras and presheaves as these generalized probabilistic theories. I'll introduce non-locality, but I have the feeling that it's not really necessary anymore after everything we've had. And then I'll go to these effect algebras and presheaves. I'll let this work. We'll make a framework, and then we'll reap what we have sown. So what's non-locality? The general frame we're looking at is we have two observers, Alice and Bob. They both have some device on which they can press one of two buttons. Whenever they do this, they perform a measurement, and they either get a 0 or a 1 as an outcome. And for example, Alice chooses a 0 and gets a 1, Bob chooses B1 and gets a 0. We can tabulate the frequencies of these joint measurements, and we can put them in a table, and we can just read that the probability of such an outcome is 1/8 because it's there in the table. So this particular table is very interesting. It's called the Bell table. It's already been shown yesterday. And the nice thing about this particular table is that we can obtain this in a quantum mechanical way, but not in a classical way. And I'll come to what this actually means. We can't just have any table. They must be, first of all, probability tables. So the sum of the rows must be 1. And there must be no signaling. So this is basically a constraint from special relativity. And we can see this as no signaling, or as a marginalization condition, or the non-locality condition maybe. That if we marginalize the fact that in these cases two blue boxes in which Bob has setting B0 and gets outcome 0, this should not depend on what Alice does. So in these blue boxes we have that Alice chose A0, and in the red boxes Alice chose A1. And this must be the same, and then we get additional constraints on these sums. So, such tables, how would we look at them? Classically, we'd consider some kind of state space, which are functions from measurement settings to outcomes. And then if we have those state space, we'd look at joint probability distributions, and we'd be in the setting of classical finite probability theory. Everything we do is finite. We hope to be able to go to some infinite setting at some point. Finite is enough for now. So what happens? We have a finite space, and we have some kind of Boolean subalgebra of measurable sets of the power set of this finite space. And we look at a probability distribution, which is just a map from this Boolean subalgebra to 0, 1, such that the whole space gets probability 0, and if things are disjoint, we can add them, and the probabilities add up. Okay. If we now look at an element in this classical space, this function state space, then this gives information about the A0 measurement as well as the A1 measurement at the same time, and quantum mechanically this cannot be if they're incompatible. So we need something more general than just standard probability theory. Now what we can note is that this probability distribution map makes basically no use of this X as a surrounding space. It only uses the disjointness of these sets to have the addition So we can replace this Boolean subalgebra by something that captures this measure only once phenomena. So the fact that if we have a measure on, if we measure A1, then Alice cannot do this, cannot know anything about the A0 measurement. Now, we do this as mentioned with effect algebras. What's an effect algebra? We just saw, but here it's again. An effect algebra is a partial commutative and associative monoid with an E, a partial sum, and a zero which acts as a zero, such that for every element there's a unique ortho complement, which if you add those two, they give 1, and 1 is defined as the ortho complement of 0. And it has a certain 0-1 law, that if something is addable to 1, it must be 0. And then we get a category of effect algebras, and an effect algebra morphism is just a map between the underlying sets, such that the sum and 1 are preserved, and it then follows automatically that also 0 and the ortho complement are preserved. And this partiality, the fact that it's a partial commutative monoid, is very important. So, why do effect algebras work? Well, this sub-Boolean algebra we had, together with, we can take unions if things are disjoint, and then the empty set and the whole set as 1. This is an effect algebra. But what also is an effect algebra is the unit interval, where we can sums if they don't, where we can take sums if they don't go above 1. And if we now look at a probability distribution, this is precisely a morphism of effect algebras. So this is, aesthetically, this is very nice, because now our probability values are in the same category as our spaces. So that's what we would like to say. An effect algebra is a generalized measure space, or generalized probability space, and the morphism towards this 0-1 interval is a probability distribution. That's nice, but it doesn't cover everything. So because we use 0-1, we only have probabilities and not possibilities. And there's other work on this, most notably the work by Abramsky and Brandenburg, and we would like to link in with this. So we have the work of Abramsky and Brandenburg is about presheaves, and we would also like to see how presheaves work. And presheaves also give a notion of a generalized probabilistic theory. So if we look at this omega again, this is a finite Boolean space, and therefore it's the isomorphic to the power set of some set of n elements. So we can identify an n element set with a natural number n. And then a probability distribution is the same thing as a map from this finite set to 0-1, such that the values of the sums of all the elements add up to 1. Well, what can we now do? We define a certain space of all these distributions. Should come as no surprise. Distributions. And this extends to a functor from this category of natural numbers and just functions. So functions between sets seen as natural numbers to sets. And by the Uneda lemma, we have the fact that a representable, one from n to something, the set of natural transformations to this distribution functor is isomorphic to precisely the space of all distributions of an n element set. And therefore we can say that functors from natural numbers to sets are measure spaces, and natural transformations to the distribution functor are probability, generalized probability distributions. So it's, yeah, we get presheaves over n, and now we can note that, or actually we get sort of co-presheaves over n. So we get presheaves over n op, and n op is isomorphic to the finite booleans. So we get presheaves over the booleans, basically. And this, the booleans are kind of the classical thing, as we will see. And then the presheaf, the free co-completion here over, there over, gives this other notion of generalized probability. Well, we now have two different views of, two different generalizations of probability theory, and we want to connect them. And to do this, we say what is a test in an effect algebra. An n-test is just a tuple of n elements which will sum to 1. And we can take everything because this sum is only partially defined, so this has to be something defined. This gives us a test functor. So given an effect algebra, we can look at all the, given an effect algebra and a natural number, we can look at all the n-tests in this effect algebra. And this gives a functor from the effect algebra to the presheaves. And this one is full and faithful and has a left adjoint. This will be useful later. And it's the test functor. Okay, so now let's see how these effect algebras and presheaves work for non-locality statements. What we can do is we give Alice an effect algebra. What is it? It's just her settings, including outcomes. So we have the blue ones, which are the 0 settings, and they have different outcomes. So there's the 0 setting with outcome 0, there's the 0 setting with outcome 1. And these are each other's complements. These add up to 1. And likewise, the magenta settings, they also add up to 1. But we can't look at a blue and a magenta one together. They're disjoint, as it should be, because once we know something about A0, then we could not have actually measured A1 instead. Well, likewise, we define a effect algebra for Bob. And effect algebras have a tensor product. And if we then take the tensor product of the effect algebra for Alice and the effect algebra for Bob, this is again an effect algebra, and it has elements of a form like this, where we have one outcome for Alice with a certain measurement, and we have one outcome for Bob with a certain measurement. We can also define Boolean algebras for Alice and Bob, and these are basically the function spaces we had previously. So this has information about the 0 measurement and about the 1 measurement. And we can think of these as kind of hidden variables for Alice, and likewise for Bob. That if we have such an element and Alice performs one of the measurements, then he or she gets the answer which is specified by such an equation. And we would like to note that the Booleans, this Boolean algebra, kind of the free completion of these effect algebras into a Boolean algebra. Now, what's now the case? If we have a no signaling probability table, then this corresponds precisely to an effect algebra morphism from the tensor product to 0, 1. And this also corresponds to certain biproducts, if you happen bimorphisms, if you happen to know what those are. But the fact that such a table precisely corresponds to amorphism is very nice because now we're completely in this category of effect algebras. Okay, now we say that a table is classically realizable if it's vectored through a Boolean algebra. So if we can find some distribution on the Booleans such that the table is recovered. And we say it's quantum realizable if it's vectored through projections on a Hilbert space. Well, a projection on a Hilbert space is basically a yes-no question to the system. And now, what we would like to say is that this table does not factor through the Booleans, so it's not classically realizable. So this is the case for the Bell table, but it does factor through this quantum setting. In this quantum setting, factors through the projections on a Hilbert space, and this is kind of the paradox. Now, if we have any adjunction, then we can, and we have a non-factorization, then we can transport this non-factorization to the other category. In particular, if you remember that the test functor had a left adjoint, then we can go from this effect algebraic description to the presheave description over here. So we have some sort of tests which map now to the distribution functor, which are precisely the tests on 0, 1. And we can transport this non-factorization to presheaves. Well, we would like to work relative to this object of the Booleans. So we can take slices here. And we get this presheave category sliced over the tests on these Booleans. And these Booleans are, the tests on the Booleans are precisely representable functors. And if we have a slice category, then we always have an adjunction like this, from the original presheave category to the slices thereover. And then we can use our formalism again to transport. And we have that, well, basically, we get a non-factorization in this slice category. But what happens now is that here we have the tests over the Booleans together with the identity. And this is the terminal object in this slice category. So what we can state is that these maps, the table, are local sections, and they don't have a global section via the terminal objects. So this is in the Grothendieck story. So this is very nice. We can tell the story in this categorical framework. We can do more. So if we have more adjunctions, so we have a whole chain of them, we can go from effect algebras precisely to the category that Abramsky and Brandenburger use, and then we find their work. We can also not consider effect algebras, but something slightly more general, called pointed partial commutative monoids. And then we can also do this probabilistic calculations, like the Hardy table. And if we not slice over the Booleans, but slice over the projections of a Hilbert space, we can find Cauchy-Specker, the Cauchy-Specker paradox. And so I'll leave you with this slogan that different contextuality scenarios arise from different slices of this presheave category over the Booleans, basically, or the natural numbers.
Thank you. What's the tensor product of effect algebras? How much do we think about that?
Okay. So, if you want to know in general, you have to read a paper of Bart. In case of these easy effect algebras, they have these elements, so the combined elements, and there's a certain, you have to say when something is a test, so when things are summable. And it turns out that this is precisely the kind of hypergraph that was shown in the first day by Anna. Yeah,
All the non-signaling.
yeah. So non-signaling is built in these effect algebras, in these tensor products. If you take the tensor product, you automatically have non-signaling, and that's this theorem.
So is it analogous to this kind of maximal tensor product you get? Oh, wait, maybe you don't know.
No, there's only
Generalized probabilistic theories.
Here it is being
So if you're familiar with the hypergraph formalism, then this tensor product corresponds precisely to their non-signaling tensor product of the graphs.
So we saw yesterday in the works of Abramsky and others that they introduced at least here, I remember 3 contextuality, right? Contextuality, logical contextuality, and strong logical contextuality. Do you have like the same corresponding things in your slice category or structure?
No, that's a good question.
Yeah.
We also want to look at this, but as far as I know, this you basically look at, you go back a step to the effect algebras or to the normal thing, and you check if there's strong contextuality or logical contextuality, and then you say, well, also in the other case. And I think we also have to do this here. I'm not aware of anything that says if you have these local sections, then it's one of these contextualities.
Thank you.
Is this framework a new way to phrase the paradoxes? Can you also use it to find new proofs of the paradox?
That's also a good question. I think it's a new way to phrase them. But it seems that, there's this transporting going on. It seems that if you can find anything in this, you can also find it in the other.
Yeah, exactly. So my there's another proof that uses presheaves, for example.
Sorry?
Yeah, so it might be that there's another proof that uses presheaves, for example.
Yeah, that could be. I'm not really sure. It would also be nice to look at cohomology for this.
Can you say just a little bit about the left pathway you constructed for the test? Is it just
Okay, it's for the test function. It follows from general reasoning in this book of McLean and Moerdijk, because effect algebras are co-complete. There's automatically.
let me rephrase my question quickly. Does it coincide with the construction of the effect algebra, from sort of generalized test space, taking quotient by perspectivity?
I've never heard of that construction. I don't know.
Okay.
But I would like to talk about this afterwards.
Okay, let's thank Sander again.